We saw this notion of two universal hash families.
Equal to 0 to such that every x in U T
There is a family of functions such that if I pick a function uniformly at random from this family, it has these two properties. Okay. So it takes an element and it uniformly spreads it to any of the table locations with equal probability, and the collision probability is also very small. So using this, we came up with the solution for the data structure problem, dictionary problem, where the expected time for any of these operations is constant.
We also saw an interesting application of this small sized hash family for de-randomizing application algorithms. Okay.
So what we showed yesterday was showed a construction, algebraic construction of a small sized two universal family. Small size because size is p square. Roughly p square compared to t power p, which is the size of all functions from u to t. Okay, so often hashing is used as a solution for good randomized solution for searching insertions and deletions. But at times we are also interested in the worst case constant solution. So the question you are interested in is, given static set S, I'm interested in constant worst case time. I'm allowing only linear size data structure because if space is not an issue, we have a constant worst case time structure, right? What is that structure? If I don't worry about space, characteristic vector of the set, which uses space M, right, is a constant time structure, right? Uses a lot of space proportional to the size of the universe, whereas I want to use space proportional to the size of the set I'm representing, okay, and still be able to answer questions in constant worst case time The universal hash family gave you a structure where you can answer questions in constant expected time. But expectation is over all these hash families, hash functions in this family. Okay. Now, why should such a structure exist? Right? I mean, we also have an order n sized data structure where the search time is not constant. What is that structure? All I care about is membership. I give you n elements. I'm allowing you only space proportional to linear in the size of the number of elements. How would you, if you don't worry about time, if you don't worry about space, characteristic vector is a nice solution in terms of time. If you don't worry about time, but I want a linear sized data structure, what do we know? This is just a dictionary problem. So you know how to solve this very efficiently. And all I care about is membership. I'm not going to proceed if you don't answer. This is just a trivial first lecture question. We did it in first lecture. I give you n elements. You are allowed to organize it in whatever way you want. I care about membership. I don't care about time, but I care about space. You are allowed to use only, space proportional to the number of elements. Array, and what do you do? Just keep it sorted, no? Binary search. Why is it taking so long? Because we saw some complicated structures along the way. We forgot all of it. If I don't care about time, if I just give you n elements and say organize it whatever way you want, I want to support membership, you should know at the back of your head, right? Just keep it sorted and do binary search. You know that. But binary search takes logarithmic time. But I am asking for a constant worst case time. Okay? So why is this possible? Well, I tell you there is a size bound on the size of the universe. So something you can make use of. And we did extensive hashing last time. So I want to map this entire universe into an order n size table. Such, right? Universe size is really large, much larger than n. I want to come up with a function that maps this entire universe into a small size table, such that on this set, this function is injected. It maps this set without any collisions. Yeah. So out of all the hash functions or functions from this universe to an n size table, first of all, are there such functions? So let me ask this question again. Right? Let's think of not just are there lots of such functions. So look at all functions from this universe to n size table, out of which I give you the set S. I want this set to be mapped injectively, meaning without any collisions. Can you tell me how many such functions are there? There are lots of such functions. Right? What do I want? I want this, let's say 1, 2 or 0, 1, 2 up to n minus 1. So these elements, I want them to go here without any collisions. The rest I don't care. Okay? So how many such functions are there? N factorial into, for the remaining m minus n, you can just go and map it to any of the n locations, or n power n minus 1. And these n elements, map them uniquely in one of the locations. There are n factorial ways of doing it. The remaining m minus 1 elements, just go and map it to any of the n locations. There's so many such functions. Okay, that's what makes us believe that we could come up with a function where this set S, which I want to represent, is mapped injectively. Okay. There are lots of such functions. The question is there a nice representation for this, right? The beauty of this family of functions is, given an x, I can compute h of x very easily. Hardly involved anything. Ax plus b, that's all. I remembered an a and b. So once you give me an x, I multiply by a and add b. That is the beauty of this function. So question here is there a nicely computable function which I can store? Maybe I store a and b or some values, some combination of values. That moment you give me an x, I will apply this function, and this function is mapping the elements of this set injectively. So you can choose the function based on the set. I give it to you in advance. I give the set in advance and tell you that this is the set I want to represent. Can you come up with a function that depends on this set, which maps this set injectively, and still you are able to compute it very efficiently in constant time, right? Because if I give you the set in advance and say, tell me a function which maps this injectively, no problem. I take the first element, smallest element, map it to the location 1, second smallest element, map it. So that's a function which depends on that set. But how do I check membership, right? When an x comes, what is h of x is not so easy to figure out. So I want a function which is nicely computable in this sense that at constant time I can evaluate it and check for membership. Okay? And so there's a very beautiful result due to Friedman, Homeless, and Zemerity. It's often called FKS table or something like that, which basically answers this question, saying yes, there is a way to store your given n elements in linear space and still answer membership in constant worst case time. Okay. So you're going to come up with such a function. So keep in mind that this function can depend on your set S, because S is given to you in advance. Okay, and that's going to actually use two universal hash families, and more precisely this construction. Okay, so F, always keep in mind that your set is given to you, a fixed set, right? And suppose I pick is randomly picked from this family, which we will call as so I take some function from there, randomly picked, and hash S and see what it does to S. Okay. So the range of this function is 0 to t minus 1. So elements of S get mapped to various locations. So let's call Bi set of all element in S such that h of x is equal to I. So all elements that get mapped to location I. Okay. And I'm looking for a function where, let's actually call this capital Pi and Pi. I'm looking for a function where these Bi's are expected to be what? I want a collision-free function on this set, yes. What does that mean? What do I want Bi's to be, little Bi's to be? 1, right? I want Bi's to be 1. I'm trying to see, is there a function f of course, I want T to be linear in N. I haven't chosen T yet, but T I want to be order N sized. So if I choose T to be some order N, is there a function where all the BIs are 1? That's the kind of question I'm interested in. Okay. So let's use some properties of the true universal family, and let's compute the following. Right? I just picked a random hash function. So expected number of collisions on the set S, on S. Pick a random function and I'm applying it on the set S, and I want to see what is the expected number of pairwise collisions. Right? Summation x, y, set x, y, and S, x not equal to y, probability that this is what I'm interested in. Right? This is the expected number of collisions. What is the collision? To a pair x not equal to y, but they get mapped to the same value. And what is this? By the property of the true universal hash family, we know that this probability hx equal to hy is at most 1 over t. That's the property of this true universal hash family. So that I choose two values. Okay. Right. Now can somebody tell me another way to write the number of collisions in terms of the BI values? In terms of the BI values, what are the number of collisions? Pairs which are collided is what I'm asking.
For each I, BI minus 1 is number of collisions.
Okay, for each I, how many collisions are made?
BI minus 2. BI minus 2.
BIC 2. Every pair in that set contribute to the collision. Right? Because they all, every pair here has x of x equal to x of y equal to I. Okay. Remove the 2 from both sides. Okay. Now, what is this one? Summation BI. Summation BI I equal to 0 to t minus 1. N. Because all elements of your set get distributed into B0, B1, B2, B3 and so on. So together there's just N, right? So square is less than equal to T is still my choice. I haven't chosen what my T is. Ideally, I want it to be linear in N. So now I'm going to write a couple of lemmas and then I will. is n square, then let the value of summation bi square what does this mean? That summation bi square, summation bi is equal to n. You know that. Summation bi square is less than or equal to n plus 1 means what? Bi cannot be greater than 1. Each bi is actually, I mean, the expected value. We are looking at expected value. Then the sum of the squares of these guys is less than or equal to n plus 1, because even if any one is like a 2 instead of 1, that contributes, the square would contribute 4. Huge extra it will contribute, not, it cannot be plus 1. Okay? So what does this mean? This is a corollary one, right? There exists an h in, what did I call that? FPP. Which is injective on S. Injective meaning collision 1, 1. When t equal to n square. Why? Because I expect there is the expected value of the summation bi square is less than or equal to n plus 1, means that there is some function which actually makes the summation bi square less than or equal to n plus 1. That function is the one which makes this injective. Because bi's are all 1 means what? There are no collisions. Right? Summation bi square is at most n plus 1 means that there is some function, because average is at most n plus 1. So there is some function which makes summation bi square at most n plus 1, which means that there is some function which makes all the bi's to be 1. Which is what I want. Right? I want the bi's to be 1 means that there are no collisions. But we haven't solved the problem yet, right? Why not? T is n square. So this says that if you allow your table size to be n square, then there is some function which you can find which will map everything in your set injective. Okay. Okay. Let's write 2 T is n. Minus 1, you can put t equal to n, n plus n minus 1, which means again a corollary is there exists a function some reason lots of such functions. I will pick any one of them. I'm going to call it HMN. I'm going to use it. Similarly, here when I pick T to be n, there may be lots of functions where makes the summation gi square. I'll pick any one and call it S. I'm going to use both of this to come up with a solution for our problem. So that. So you see the problem. If I allow myself a table size of n square, then I have a perfect hash function which will map it injectively. If I allow myself a table size of n, then there is a function which makes the sum of the bucket squares to be linear.
Okay. So now we want to put this together to get a solution, and the idea is to use double hashing.
I want to see whether anyone already sees the solution. I'll just give you a minute to see whether you put together these two corollaries to answer this question. So here is there. Yep. Okay. Here is their idea. Beautiful idea. They say okay. So I'm going to use this portion to store the hash function. Let's see what. So first thing what I'm going to do, I will keep my table size to be n. Okay, I'm going to keep my table size to be n and pick up this. Pick up this function. So don't worry about the pre-processing time, how much time it takes to find such a function. That's not a problem because there are only some p square and I'm not so much worried about the pre-processing time for now. Okay. So you just go over it, run each function at a time, hash it onto your set and see how it happens. Pick the one, pick any one which has this property that summation di square is of course n. So I'm going to use my t to be n to start with. And store this function hn. Okay. So an element comes, I apply this hm function, and the property I know is that it's not perfect hash function, but it's going to create these buckets, but the bucket squares together is at most 2n. Okay, it's fine. So I'm going to allot space proportional to b0 square here, b1 square. This is the space I'm going to allot. Okay, so an element comes and I'm going to apply my h of m of x, and that's going to take me to some location I. Okay, and it's going to be making collisions because I know that the BI is not necessarily 1. So now I'm going to see how do I put things inside BI, right? Okay. I have allotted BI square space. And my corollary, the first corollary says that if you allot quadratic in the size of the set, then there is a hash function which will map it injectively. Right? So I look at all elements that go into that bucket. Now that's my new set. How many elements are there? Bi. And I'm allotting Bi square space. So there is a hash function which will map all these elements injectively in that Bi square space. Okay? So I'm going to call that Hs, but one for every. So I'm going to store here Hs0, Hs1 for each bucket. So now I will take my HSI function. So h of x, where does it go? Well, suppose h of x is I, then I minus dl square l equal to 0 to I minus 1 plus HSI of x. That's going to map it injective. Because I have allotted quadratic space. Is it clear? So I am doing double hashing. The first hashing is using the hash functions from the second corollary. It says that there exists a function which makes sure that the sum of the bucket square is linear. Okay. Then the second function, so it tells me, okay, go to some location I, because my table size is n, so it's going to take you to location 0 to I minus 1, n minus 1. And in that, where do I go put it? Well, I apply another hash function which maps things injectively if I allow quadratic space. So in that, I'm going to map somewhere injectively my element. So the total I allot, so now all this can be looked at like a one-dimensional array, right? Where the first so many elements, locations are for d0 square, d1 square, and so on. So within the I table, I allot I minus summation bl square space is gone, plus in this I apply the secondary hash function, go put it. Here's a clean injective hash function. And how much space have we used? Where is 3n? N for the hash. So I have used 2n space because summation bi square is the same that I used, that is 2n plus 1 plus n. 1 for the primary hash function, n for the secondary hash function, and then there is 2n. Plus, if you think about it, I also need to store this because if I want to find its location in constant time, I also need this partial sum of the squares. So that's also another n such values, right? So summation that's some n. Together now my element is mapped injectively the total space used is order n. Well, for the summation bi square is about 2n plus n plus 1 for the hash values plus another n for the partial sums of the squares. Okay? Is it clear? How many people did I lose?
Divide and conquer in the same order. So that instead of mapping it injectively in your first hash function, you can allow say some constant in each bucket from your static system. And then this secondary hash function will map it again injectively.
Let's come to that. But I want to make sure that this is clear. And everyone understood this. What's the problem? Yeah.
They applied it here to show that the expected value.
So look at corollary 1, corollary 2. Okay. The way to interpret each of this corollary is that they are all from the same universe. Universe is 0 to p minus 1. Corollary 1 says that if you give me quadratic in space, quadratic in the number of elements you are trying to represent, then I'll give you a hash function which will map things injectively. That's what corollary 1 says. T is n square. If your table size is quadratic in the size of the set you are trying to represent, then I can map the set you are trying to represent. I will map them injectively. Use this hash function. This says that if you use t to the n, then there is a function which may not map it injectively, but it maps it in a way that sum of the bucket squares is at most 2n. Okay. So now I'm going to use this as a primary hash function. So it just says sum of the squares of the buckets is at most 2n. And for each bucket of size bi, I allot space bi square. and apply this hash function. And this will map all elements coming into that bucket, it will map injectively because I have allowed quadratic space. So there are n such secondary hash functions I am using. One primary hash function and n secondary hash functions. Okay. The total space used is summation bi square, which I know is bounded by 2n microarrays. So this is primary. And this is secondary. One for each bucket. I going from 0 to n minus 1. So the first bucket has B0 square space and then B1 square space for second bucket and so on, and total thing is about almost 2n. Yeah, so now let's come back to what you see. Yeah, what do you say?
Instead of marking the first one injectively,
I'm not mapping first one injectively.
your primary hash,
It's not mapping injectively.
the set, it mentioned.
That maps things such that summation bi square is at most 2n.
But within each bucket is not.
Within each bucket, I apply another hash function.
But your primary hash function doesn't mark within each bucket injectively.
No, it does not. Because bi is now, I don't have a guarantee that bi's are 1. Primary hash function says this. Summation bi square is 2n at most. So some bi's may be 10, some bi's may be n, all kinds of things can happen. Well, it can't be n, but it can be root n, bucket sizes can be completely large. So one word about the pre-processing time, right? How do I find such functions? Right? If you don't care about pre-processing time, then you can actually go over, there are only p square such functions, run them all, test it on your set and get it. But from this expectation argument, one can argue that, let's say if I choose t to be 2n square, then the expected value is even half of this. Right? If I just go 2n square instead of n square, the expected value is even half. It means that not one, there may be at least half the functions will have the property that there won't be any collisions. So you can actually apply some randomization, randomly pick your ABs, and quickly you will get something which satisfies what you want. And the same thing here. If I, instead of n, I apply 2n, and the whole thing will increase my constant in this order n size, right? This constant will increase because now it's no longer n square but 2n square and so on. But the payoff is that I can quickly find these functions. The pre-processing time I can save because I'll just randomly try a few things. Many of these functions satisfy this property, so I'll be able to get them quickly. Okay. Now again, so this is actually in CLR, by the way. It's not both today's and yesterday's lecture is in the hashing chapter of Polynomials. So this family of functions is called perfect hash family, and what we saw yesterday was universal hash family. So what is the perfect hash family? I mean, what is the hash function we are using? I mean, what are the things I need for the hash function? Well, I need all of this. I need the primary hash key, the secondary hash keys, the partial sums, and all of this together will constitute one hash function, because I need all of it to compute my h of x. Okay. Now, one can ask this question. Okay, so what have we let me write the claim again in a different way, what we have done. So instead of looking at it as a data structure question and a solution, I mean, towards that end, this completes it. Okay, this is the question I'm interested in. This whole exercise we have done it. We give a nice complete data structure solution to this data structure question. But you can think of it as a hash family. What is a perfect hash family? It also has a lot of parameters. So let's. If for every subset S contained in U such that fragmented as N, there exists a H in N that maps S injective. Right, I'm actually being very stringent here. I earlier allowed order n size table, now I'm saying no, I'm just going to give you only, I want you to map it to exactly to n values. Okay, I want a function which goes from this universe to a table of size n such that this function is over this entire universe. If you give me any set S here of size n, then there must be some function here which maps the set S injective. Okay. In fact, we did a quick calculation. We saw that there are lots of functions. If I pick all functions from the universe to 0 to n minus 1, then n factorial into whatever n power p minus n such functions are there. If I use all functions from 0 to u to 0 to n minus 1. But I am interested in the small size perfect hash family. Okay. So the fact that there is a perfect hash family exists is clear, because if we use all functions from u to 0 to n minus 1, there are enough functions which will, given any set, there are enough functions which will map injectively. The question is, there a small sized hash family, and that's in a sense that's what we did here. If we convert this whole thing, and it requires a lot more work, so that's not the end of it. The claim is that there exists perfect the size of all families is, what we saw was that n power p total number of functions. So there is such a hash family, I mean the entire family of all functions. There is one of size n power p, but what this is saying is that if you actually take this FKS table and do a lot of range reduction, there is a lot more, you're storing a lot of things here, but you can optimize on the number of values you store, because one secondary hash key may actually work for several of the buckets. Now we are storing one for each bucket, we can improve, and then the size of these values can be reduced. There are a lot of range reductions and some more work that can be done, and if you convert that eventually, that gives you a perfect hash family of size something like 2 to the order n into polylog in p. Okay. So this is a nice result which starts from FKS table, and with some improvement we can get this. Now just like we had an interesting de-randomization application for a 2 universal hash family, I want to give you an application of such a hash family. Okay, again for de-randomizing some randomized numbers. Yeah. So that's the problem I want to. Okay. So that's the end of the data structure question. FKS table. We've solved that. Now I want to convert this whole thing into this kind of a statement where I'm looking at a small sized perfect hash family. So is it clear what a perfect hash family is? Right? It's a family of functions from U to n, such that if you give me any n element subset of the universe, some function will map it injective, one of these functions, and it's a small size. Okay. If you want to give an application in parameterized complexity for such a small size hash. So the problem I want to look at it is that given a graph G and an integer k, does G have a simple path of length k? Undirected graph. So this is an NP hard problem. Why? Hamiltonian path, the longest path. Right? I can't expect an algorithm which is polynomial in n and k. Okay. And there's a very easy n to the k kind of an algorithm. So n choose k into k square. Try all possible subsets of size k and see whether they form a simple path. Is one output. You can think of how you might use BFS, DFS kind of things, but the problem is to keep track. It's a simple path, right? I'm keeping track of what vertices I have seen, and then going to k levels typically will end you into an algorithm of the type n power k. Okay? Sorry?
Does it order matter to the
Does an order matter?
combination?
Okay, so what do you want to add? K factorial or something? I mean, I choose k vertices. Oh, I see. Okay. Okay, so conservative algorithm would be like fix also a permutation and check whether there is, in that permutation there is a path. Then you don't even need a k square. It's a permutation, and then check whether there is a path 1, 2, 2, 3, 2, 3, 4, 4, whatever. Okay, you can think of other algorithms, you know, take the adjacency matrix, take it to power of k, all kinds of things. Eventually, you will end up with an n to the k algorithm. So the question in parameterized complexity one is interested in is it an FPT? Right? Is a fixed parameter tractable? What does that mean? What kind of an algorithm are you looking for? Yeah, so I am interested in ID. Is there f of k times n to the c algorithm? It's a very beautiful algorithm. I mean, that question was answered yes by Allen, Easter, and Zwick. It's a very nice paper. I would encourage you to read this. Anybody interested in randomized algorithms? Reasonably accessible, very nice, powerful technique. And so here's the algorithm. Step 1. So it's a randomized algorithm. We're going to give a randomized algorithm first, and then we will use this to de-randomize it. So randomly color the vertices by colors 1, 2, 3. Okay, so this has nothing to do with graph coloring. I'm just labeling the vertices. I choose a k-sided dice, toss it, and for every vertex, whatever value comes, I go and assign that. So vertex 1 will get 5, vertex 2 gets 3, whatever. So k colors are assigned to all the n vertices randomly. Every vertex gets one of the k colors randomly. So just a labeling of the vertices. Step 2 is find a colorful path of length k. So what's a colorful path? It's a simple path where all the colors are distinct. The colors are distinct, the vertices will be distinct. Right? But if the vertices are distinct, need not mean that colors are distinct. Okay? So I'm going to find a colorful path of length k. I'll tell you how to find it. Okay? We will do a dynamic programming, and it's a very nice simple algorithm. So that is the order. In order 2 power k times m, we will branch off and look at this algorithm separately. So if I found such a path, I am done, right? You want a simple path of length k, here it is, right? If I don't find the colorful path, so if found, output it. Else, that is, if I don't find a colorful path, go back, do another random coloring of the vertices, and find a color. Keep doing this. Okay. Fine. So let's. So that's a randomized algorithm. Nothing else going on. Randomly colorful path is a big subroutine. I'll explain you now. And then after that, if you find it good, that's a simple path. If not, see, if you don't find it, you can't say no, right? Why can't you say no? Yeah, I might have a simple path of length k in the graph, but the coloring has colored some of the vertices as the same, so it's not a colorful path, right? So this guy is trying to find a path where all colors are distinct. It's possible that the original graph had a colorful, simple path of length k. This coloring had messed it up, made two vertices of this path the same color, so this dynamic programming algorithm did not find it, but I can't simply say, oh, there is no path of length k. So just go on. And the goal is that now you can go and relate to the hashing question. That if there is a simple path, one of these functions will actually color it with all colors distinct, and this algorithm will find it. That's my goal. Okay, let's analyze this algorithm, and we'll see how to de-randomize it. So let's take step 2 and look at it carefully. It's a very simple dynamic programming algorithm. So first, we will find a colorful path of length k if it exists, starting at a vertex. I'm going to modify that. I'm not going to find the colorful path of length k in the whole graph. I'm going to find the colorful path of length k starting at this vertex, some vertex. Right? If I manage to do this, I can solve that by doing what? Start at every vertex is one solution, so multiply by n. Or you create a dummy vertex which is adjacent to every vertex and give it the color 0 or something, new color, and start from there. Okay? So it's enough to look at this. So this algorithm is going to have multiple stages. Stage I. Okay, so before that, at each vertex x, store set SI. What does SI contain? A color set C contained in SI if there exists colorful path. And then we write it down and explain. It's not very hard. Length I from S with color set C. Read this. At a node x, at stage I, I'm going to store a set Si. What does it contain? It contains some color sets. Okay. What are these color sets? Well, the color set here means that there is a path of colorful path length I starting at S, ending at this vertex, with colors in that path being this set. There may be several paths, colorful paths from S to I. So I store the color sets of each of these. For every edge to B, exactly what we need to do. So what is this? So I look at an edge UV. This is at stage I plus 1. What do I want at stage I plus 1? I want color sets of paths of length I plus 1 stored at every vertex. That's the invariant I want to be doing. Right? So I look at the edge UV and say, okay, U has a lot of color sets here stored at stage I, right? And see whether any of these sets does not contain color of V. If not, I'll take that set and color of V and add it and I put it here, because at this point I know that there is a path of colorful path of length I plus 1 ending at this vertex with the color set that color plus this, because that's this one. Put it. That's all it's happening. Okay, and that's it. Just keep doing it, and you go through some n stages. No, k stages, because I'm looking for colorful paths of length k, and finally, look at sk of any vertex. If it's non-empty, you know that there is a colorful path of length k. Okay, and this is the essence of the work. How much time does this take? Well, for every edge, so it's m times. How many color sets can there be here? How many sets can there be here? Maximum. These are all I element subsets of k element colors. So at most k choose I, right? So essentially summation k choose I that's the number of sets you are going to look at and compare, combine and see what you want to do. So essentially, so very simple dynamic programming algorithm. It checks whether there is a colorful path of length k starting at a vertex. Which also means, I'm trying out every vertex, you will check that there is a colorful path of length k. Okay. Is that clear? Okay, some bookkeeping, but nothing deep going on. Once you figure out what you need to store at every set, at each stage, how do you update, what is the starting point, everything becomes clear. So now let's go to step 3. Suppose G has a simple path of length k. What is the probability that, call this path P, what is the probability that P is colorful? I have a simple path of length k. What is the probability that all these get different colors by my original random coloring? Each vertex gets one of k colors. There are k vertices. What are the total number of possibilities in terms of colorings? K power k is the possibilities. And which ones are good? K vertices in this path, right? Each is getting any of the k colors. So there are k power k possibilities. But the good situation for me is any of the k factorial, all of them getting distinct colors. So this by Stirling approximation for k factorial is 1 by e power k. So, what is the expected number of times I have to run this algorithm to find such a path? E power k, right? If you toss a coin, probability of head is half. That means expected number of times I have to toss to get a head is 2, right? Similarly, the expected number of times I have to run this algorithm to find such a path is e power k. So expected So, if you really want a good probabilistic algorithm, run it some 2 e power k times or 5 e power k times, and if you don't find it, you say no, and you will have a good probability of being success. And what is the total running time we have spent now? Each time we are spending only 2 to the k m times. That's the this dynamic programming is 2 to the k times m, and we are repeating it some e power k times. So the whole thing is some 2 e power k times m. So that's that kind of number. F of k, right? Some so that's expected running time. It's a randomized algorithm, randomized FPT algorithm, right? Nothing. I mean, it's very powerful, cute idea, but the algorithm as such is very simple. Randomly color it, find a colorful path, repeat, and you have a good probability of finding a colorful path if there is a simple path. Now, how do you de-randomize this algorithm? Well, what do I need? De-randomize means I don't want to repeat forever. I want to be sure that I will find a simple path if there is one, right? How do I find this? Because I'm just applying colorful path algorithm. So, if I try a lot of, what is a labeling? A labeling is a function from 1 to n to 1 to k, right? It's just a function from 1 to n to 1 to k. So, if I have a family of functions from 1 to n to 1 to k, small sized, with the property that if there is a path of length k, one of these functions will actually label it in a colorful fashion, right? But perfect hash family does exactly that, right? What it does is that if you have use k n perfect hash family, use functions from so what I mean is that we have this nice family of hash functions. I take one of these functions, color it, find a colorful path. If you find it, good. If not, try another function from this family and keep doing it. But this family of functions has the property that for every subset of size k, one of these functions will map it injectively. So in particular, if you have a simple path of length k, those vertices will get mapped injectively by one of these functions, and your colorful path algorithm will find it. Okay, so it's enough to run through a perfect hash family of functions, and the number of functions as I wrote down is 2 to the order k times poly log n actually. So that's the number of functions. So we're running through all these kind of functions, and any one of them gives me a colorful path, I'll say yes, otherwise I'll say no. So my total running time now is multiplied by this is the expected, and the worst case would be another. So essentially Okay, so we don't know any other way of showing that deterministic FPT. It's a nice randomized algorithm and de-randomized. It will be nice to actually come up with a direct deterministic algorithm for that problem. So this paper, Alan Eustace-Wick paper, is a very nice paper. I pretty much explained the crux of the ideas there. But this has been applied for a number of problems. Not finding a path of length k, finding a cycle of length k, finding a tree on k vertices, graphs of tree width at most constant, various applications are there in that paper. Okay, and this is yet another application of hashing. Started off as a solution for a data structure problem, having wide-ranging applications for de-randomization.